So, okay, wait. Do that. So last week we discussed some important terminology, remember? And so these are like terms that we'll be using like throughout the class. So like our first one, machine learning, I guess. And so we understand machine learning in the way we'll be learning, which has models learning how to combine inputs and create useful predictions. And I think the three main pieces of terminology you should understand are models, and then there are the inputs, and then the predictions. And so we kind of broke those down on their own. So features, or the inputs as we might know them as, those are they're the input. And so in a machine learning algorithm, you might have one feature, or you might have tens of thousands of features. And that all depends on the data set you have and what you're trying to predict. So for example, if we were trying to predict house prices, we might not necessarily use only one feature, but a variety of different features. So some inputs could be the number of rooms, the distance to the local primary school, the number of stories in your house, or like the fourth one is like the occurrence of HIP in the marketing of the house. And so those are all inputs that could be potentially useful to a machine learning model, learning to predict house prices. And then our output, or label, is the thing that we're trying to predict. So in that previous example of house prices, we're trying to predict house prices, like the monetary value of the price of a house. But it could be anything, like the type of animal in a picture or the presence of spam in an email. So there's a ton of things that we can predict, and there are a ton of inputs to those to like make those predictions. So when we combine those in terms of data, we get kind of examples. So that's the combination of a feature and a label. And so we use those to train our machine learning systems. And so an example of a house might be that individual house information along with that corresponding price. And we use that since it's the combination of a feature and a known label, we can use that to predict house prices. And so as it puts on here, like once we trained our model, we can predict the labels of unlabeled examples, which are examples that have the feature, but not the label. And so that's the big thing, like what's a model? Remember that's like the computational relationship, or the relationship between features and the label. And so training is what we consider creating the model, and then validation is using the model on never before seen data or making predictions. And then there are two types. For our purposes, we'll be studying regression mostly. That's what we're doing today, actually. And there's also classification that predicts discrete values. Well, regression predicts like a continuous number. Does anyone want me to go over these again? I hope we.
What do you mean by like continuous models versus discrete values? Like I didn't really understand that.
Oh yeah, okay. So, like a classification, if you were predicting like in a picture whether there's a dog or a cat in a picture, those are two discrete like things you're predicting, right? So it's either a dog or it's either a cat. But for a house price, it could be a value between like 100 and like 200. And it could be any number within that range.
So basically, regression is like a range, and then classification is one or the other.
Yeah.
But why is it called regression?
Uh, that's just like the term they use.
Okay.
It's not like any like it's not like progression or regression. It's just like the type of, I think that's just what they call it.
Okay, thanks.
Yeah, sorry. Um, yeah, does anyone want me to go over the labeled and unlabeled examples? I think that might be the harder thing. So today, oh, someone put something in chat. So Andrew says classification is like going on forever, or is that regression? Regression is, as I said, as Julia put it well, it's like the range of values that you're predicting, while classification is two discrete like values or multiple discrete values. And then, oh, you want me to go over? I can go back. So often when you see like a data set, which is the set of data that you might be using to train a model, your training data set, which is what you will use to create the model, has the combination of the inputs and the labels. You need both so that the machine can understand like the relationship between the two. Because if you're missing the features, then there's no inputs. And if you're missing the outputs, how is your like model supposed to like um relate your features to some sort of output that makes any sense? So that's what the labeled examples are for, training the machine learning systems. So yeah. And then for the unlabeled, you want to test out your model on like real world examples to see how well it performs. And so that's where like an unlabeled example would come in. Because once you've trained your model, now you can use it on any number of like random houses that you find out in the wild. So yeah. I guess we could get into our lesson today, which is okay. I don't know how long this will take, but hopefully we'll be able to finish it by the end of today. So you can open up the collab for this week. You'll find it in the classwork under week 2 topic, under the week 2 topic. Hopefully you can find that. So what we'll be learning today is you'll be creating your first machine learning model. That's exciting. You'll try to understand what linear regression is. We want to understand what weights and biases are and correlate them to the mathematical equations you've learned in your algebra classes. Understand what error or loss is in machine learning. Discover how machine learning models are trained. Understand what the method called gradient descent is, and experiment with learning rates. So those are all things that we'll be doing today. So let's get started. So linear regression, as we just talked about, the regression is the class or is like the prediction of a range of values. And so linear regression is like a model that uses a straight line, or I guess plane, that best fits a set of points. And it's a good, I guess, like baseline model to understand how machine learning as a whole works. And so we can start with an example data set, and it'll be in like the 2D space. So okay, I already ran this, but you can run it for yourself. And so can everyone like do this? I want to make sure. Disregard this.
Wait, so this is like a in-class thing, right? That's a new assignment?
No, this is like the basics of machine learning. It should be in classwork.
Python Basics Intro to ML in-class assignment?
No, it's called Basics of Machine Learning.
Oh, okay. I guess I'll find that.
Awesome. Okay, people can run it. It's good. You can disregard the code.
Oh, that's the thing that says no due date posted today. Okay.
Yeah. So if you can notice here, we can talk about we can talk about our data set now. So we have a set of points, and our X value are our inputs, and then our Y value are like our outputs. So if we consider this in the terminology that we know, our X value is the feature, and our Y value is the label. And so I guess I'll ask you this. I want you to try, and I guess you can't really try it now, but like, do you think that we could create a relationship that, could we create a relationship between the X values and the Y values on this graph, on these set of points? And what might it look like? Like someone, speak out loud or type in a chat. What might the relationship between these points, or like the X values and the Y values of this graph look like?
I mean, to be really simple, you could always do that when x goes up, y goes up as well.
Yeah, so like, I guess mathematically, what might that look like?
As in like slope and like a linear function.
Yeah, that's the key, right? A linear function, not necessarily slope for now, but you could graph like a line like across this plane right here, and that would be a good relationship or good graph of the points. I think if you've ever been in like a science class, they'll ask you to do this a lot, or you'll be given points and you're expected to draw a line that best fits the points on the graph. That's a key word, fits. And so when we think about our line equation, right, we have y equals mx plus b. So we know that from, I don't know, algebra 1. Yeah. And so when we look at it in its component pieces, y is the value we want to predict. M, this is the slope of the line. X is the value of our input feature. And then B is the y-intercept. Right? But in machine learning, it's a little different. So we would call this as y prime equals w1 times x1 plus b. So some similarities, but it's the same general structure. In here, y prime is the predicted label. If you remember labels are the outputs. W1 is what we call the weight of feature one. So weight is identical to the concept of slope in this example. X1 is the feature or a known input. And then B is what we call the bias. And in our case, it's also the y-intercept. And we would call it, and sometimes if you're reading online, you would see B as also written as W0. And so in terms of actually using this model or using this equation to predict points on this graph, you would input a value for x1, and then you get a y value out of it. So you substitute x1 into the equation and solve. And so I want everyone to try this out. We have, so we have a value right here, w1 and b. So I already kind of helped you to make like a line, but maybe you could do better. I want spend 10, 15 minutes on this. And I want to see if someone can make who can make the closest, they're the best fitting, I guess. Does everyone understand that? I'll type it in the chat. Okay, I'll try this as well, and we'll see if I can do any better.
Oh, wait, if you don't mind, can you scroll up to the first one, the very first example?
This one?
Yeah.
Oh, you're trying to copy it so you can run it? Or?
Oh, yeah, I was.
Okay. If you're running this in a default environment, make sure you have scikit-learn, Seaborn, pandas, and matplotlib. Those are the basics. They're the basic packages you need to import. I can help you with that after class. Or I can do it now. Actually,
Wait, so we're not actually supposed to edit this document. We're supposed to download it first, right?
could you repeat that?
We're supposed to be downloading this file and working on it. We're not actually supposed to edit it.
I sent you no. So you can edit it in the thing.
Oh, so it won't edit for everybody else's too, will it?
Yeah, it won't edit for everyone else's.
Oh, okay. So it works that way for homework too, right?
Yeah.
Oh, okay. I thought it would have edited for everybody.
No, it's nothing like that. I send you, when I make assignments, I send everyone their own copy.
You can scroll down to that assignment what you showed us.
So has anyone created like a really good, line you
I'm
want to
not
share?
sure why, but it's not working, and no matter what I put, it doesn't change. And I think I'm running the correct cell because I'm pressing the one that says run this cell.
Oh, did you? Okay, wait. Like you have to run this one and then you have to run this one.
Oh wait, I have to run both.
Or the easier way is you could just cut the one on the top and just paste it on the bottom one in front of the two things in the cell. And
Yeah,
Oh,
or you could
okay.
do that.
yeah, I got something similar, but I got 34 for W1 and B with I got 3.
Okay. Anyone else?
35 for W1 and for B I got -1.
Okay. That's nice. Andrew got 32, 0.
I got
That's
35 and 5.
okay.
I tried to connect like the most topmost dot and then like the bottom one.
Uh-huh. Yeah. That's a good observation. How did you guys, how did you guys know you were on the right track? Or how do you know that you were, I guess, making a good graph or a good line is a better like thing? Was there
Having
any
a
like
having a relatively like even number of dots above and below, but also like I mean, say there was like a big gap on both sides of the line that you put, and maybe you want to put it in the middle, and that'd be like better than having it like, I don't know how to explain this, but
yeah.
an
That's
even
good. That's
number
good.
above and below is like not enough. You can make it better in
Yeah,
some
I mean, that's
circumstances.
true.
I
I
think
think go ahead.
I think I did mine's more like kind of found the average of all the midpoints of like the points on the opposite sides, and I think I kind of mirrored it and then just kind of found like an estimate line with my eyes.
Mm-hmm.
Yeah, and then it's like W1 makes the line go the small like the lower the number is, it makes the line go more like horizontally. And if the W1 number gets higher or increases in value, it gets kind of like more vertical. And
Mm-hmm.
B, the lower the numbers, it moves the graph down. Higher it is, it moves the graph up. So I think I just kind of used those rules and estimated.
Yeah. Anyone else want to share? I mean, in chat, or like the method to your madness? Okay, that's okay. So from what I can glean, and this is pretty common because this is what I did as well. There's like, I guess the best way to put this is that you were like checking the distance between the point and the line itself. And anything that was, and like depending on like like the line itself and like those points, you'd find the distance, and you like kind of look like whether it's in the middle, because if it's in the middle, then that means like on average, that's like the closest to where it would be like close to all the points. But like, because you can't get a very accurate line, like you obviously can't like make a line that can fit this point, but also this point as well. You just have to put it in the middle such that their distances would be lower than if it was like directly going to an outlier. I guess that's the thing. And so when you were starting out, like if you had like 0, 0, like this, and you ran it here, if you started out like this, you'll see that like this line is very far from here, and it's really far from here as well. And so you might have changed it to be like, oh, let's try 10. I don't know. Oh, it's closer. So you like, I'm on the right track because I'm closer to the points that I want to predict. And so you were like, oh, I don't know, let's put 50. And now when you changed it, you're like way too far off. It's way too steep for what you want to predict. So you put something in the middle. So that's 30. And well, that's pretty good. And you can make it better from there. And so kind of what you just did, you did like a manual training of a machine learning model right there. And so training is just simply the determination of like the good values of weights, which is what the W1 is, and the bias. And so when you've created the best possible weights, or you figured those out, or you were close enough to where, I mean, I could make it a little bigger, but it's not anything like totally different. That's the state in what we call your model has converged. And congrats, it's your first machine learning model, or your first model, because machine didn't learn it, you learned it. Anything, is there anything you guys want me to go over again? Okay. Sounds good. I guess the next thing is what we call loss. And this is like, this is really important since we were discussing our models in terms of these like arbitrary values, right? Like someone would say like, I want to be close to the actual values, right? But there's no like, and you feel like, I want to be close in terms of distance, but if we actually wanted to compare our models, we'd have to use like some sort of numerical value, right? Since by I don't know whether 30, 0 is better than 35, -1, right? How do I know which one is better? Is the real question. And so in terms of comparison, there's this concept of what we call loss. And that's what you were doing in your head, really, as you were training these models. You were trying to minimize your loss. And that's a concept that all machine learning is based on. It's called empirical risk minimization. It's essentially fancy talk for minimizing your error. And so loss or error is the penalty for a bad prediction. And it's a numerical value that indicates how bad a model's prediction is. So if it's a perfect prediction, like on the dot, like, I don't know, like this point at 0, 0, then that would have a loss of 0. But if it's not perfect, then it would be greater than 0. Loss can't be negative. That's the key. But it can be 0, which is a perfect prediction, or greater. And so the goal is to have a loss of 0 if possible, since that means that you have a perfectly trained model. Although, yeah. And so as I say here, the ultimate goal of training is to create a model that has a low loss on average across all examples. And that's what we do here, I guess. So I guess and I made a graph, I guess. Or I didn't make this. But here's like a figure of what this might look like. So we have a high loss model and a low loss model. And we have the points, and our line is like the prediction curve that we made. And so on the left, we see a high loss model where the distance between these lines is really high, right? While the distance between the line and the right is really low. And so the arrow is the penalty for our wrong answer, or that's the loss that we have. And adding all those up, we can determine the overall loss for the model itself.
Like for machine learning, it's like you teach machines to do stuff, right? But like, how do you apply this to that?
Yeah, we'll get to that. Sorry, give me a second. That's a good question. Okay. I guess the best way is when a machine learning model, actually keep that question in your head, Julia. We'll go over that later today. Sorry. Okay. Okay. And so I guess the big question is, in each of these cases, how are we calculating loss? And that's something I want you guys to put into the chat. How are we calculating loss in these questions? Or you type it in chat or say it out loud. Okay. Any answers? Just like, okay. Okay, Nathan says distance of arrows. That's correct, right? So, yeah. Okay, so I say here, I said, we can build like a mathematical function, right? This is what we call a loss function. And that would aggregate the individual losses into a single meaningful value so that we can, compare our models. And so the loss function we'll use is what we call squared loss. And for a single example, it can be described as like the difference between our label and our prediction, and then square that, right? So you take this distance and you square it, and that's our loss for that example. So for this example right here, I don't know, let's say this y is, I don't know, actually, let's do, actually, no, never mind. So let's say like this value right here is like 30 and our x says like 10. What might be the squared loss for that? This is 30 and this is 10. What's the squared loss? No. Oh. Yeah. So Justin says 400. That's right. That's good. So I guess we all understand how that might work. And so in terms of math, this is y minus y prime squared. But that's only for one example, right? So how might we, so remember how we said that we want a single meaningful value across all of our examples. And so the way we do that is we take the average squared loss for the whole data set. And so our calculation is this we call MSC, or mean squared error. So we add up all the squared losses for each example and then divide it by the number of samples. So I guess we can try and code it. So we have MSC, so this is our function definition, label, and pred. So these are lists as we reviewed last week. And I want you to calculate the mean squared error. I put solutions, don't look at those yet. If they're already open, close them. Yeah. You can do this in one line, but I think for how we know it, it'll probably take like 5 lines, maybe. So, yeah. So does everyone understand what we're doing right now? Or have any questions? Are the arrows going to be perpendicular to the line? They'll be perpendicular to the perpendicular, not to the line, but to the points.
So when I was trying to do this, I had to put an indent before the part that says don't modify this because it just gave me an error and it says you need an indent.
Oh, you mean you have to put an indent like here, like you write it out here.
Oh, I had to put an indent for the MSE thing.
Wait, for the arrows, like on the second graph, would you have like the shortest distance possible, which would be like the perpendicular, or would you just have it straight down?
It should be straight down, so it should be perpendicular from the point.
Okay.
Since it's y minus y prime, so like y minus the y, like the y value here minus the y value on the line itself. It's not necessarily like the closest distance to the line itself. Wait, Julia. Sorry. You were saying something about indenting.
The part that says don't modify this, it says that the MSE thing has to be indented.
Oh, that's because if you like run this by itself, if you run it like this, there's nothing in the label, and there's nothing in the function, right? It's an empty function,
Oh, okay.
and so it's expecting like this to be indented, so that's part of the function, but we don't. I left it empty so that you could write stuff in there.
I'm kind of confused about what I'm supposed to do with this. Like, I don't know how to code it.
Oh, okay. So I guess I can write some pseudocode. So maybe what you could do is you could loop through label and pred because they're lists, right? And you can calculate, yeah. So you loop through them. And so in there, you would, maybe you could calculate, I don't know, you'd calculate the squared loss for that, specific like index, right? Because each index is an example. And then from there, you might, like sum that squared loss into a variable. And then from there, you could like divide that sum by the number of samples in label/pred. And remember that label and pred are equal in length. Does that make sense, Julia? What you might be able to do?
I think I get like the concept, but then I forgot how to do loops and stuff. So I guess I have to do some review.
Yeah, okay. That's okay. You can look at the solution if you're like really stuck. Solution 1 is the one you might want to look at. Solution 2 is like the fancy way.
How do you look at the solution? Because I can only run it.
You can double click on it. Oh,
Oh,
yeah.
Okay.
Okay. Does anyone want to share their code?
Oh, it says that list object has no attribute called len, so I'm so confused.
in
Does it have a
this
count?
in the solution.
No, like when I was running my code in Jupyter, it says that I got an error because list object has no attribute called length. So what attribute does it have that like asks for the total count?
Oh, for lists,
Yeah.
for all lengths, it's like this list.
Oh. Okay, so that I think that I put it in the wrong syntax.
Yeah, just
Yeah,
the wrong syntax.
I put in like a Java sort of syntax, but I keep forgetting that it's not Java.
Yeah,
Thanks.
welcome.
Okay, so I think I managed to get my code working. It showed something like 147 or something. It displayed like I asked it to print like my final value and it printed like 147.8.8 or something. Is that like true or something? Will that work? Yeah, you're
Yeah,
muted.
well, what were your like the weights in your what the weights and stuff?
Oh, the weights, the weight which I put like W1 equals 32 and B equals 0.
Okay. So see, like you can run this here, and I can check. So what does my solution say? Yeah, I say I got 147.081.
I got 147.899.
I guess that's because. Oh, what?
So what's the last part of that answer? It says return sum squared errors divided by length of a label. What does that mean? Like, what
In
did
the
I do?
solution?
Yeah.
Okay, so this is like essentially what I did here, or this is like the pseudocode I wrote. So I made a variable called sum of squared errors, and so I iterate through label. Actually, I iterate through the index of label, such that I is like a number or the index from like 0 to 100, right? And so when I call label I get the number at index I in label. And so this means that I have the corresponding label and the corresponding prediction. And so I minus that and I square it, which gives me the squared error. And so I add the squared error to this running like sum variable right there. And so when we say average, right? To calculate average, we have to add up all the squared losses and then divide by the number of samples. Because remember, mean is that's what mean is, the average. And so once we add it, you have to divide by the length of label, because the length of label is the number of samples. Does that? I assume that's still really confusing, right? Or
I think I can understand like how it works by looking at the code, but then like I have some trouble making it on my own. So then practice, I guess.
My current state as well.
Oh, wait, what would you say, Sophia?
So it kind of feels like I get it when I look at the code, but I'm not exactly sure how I'll be, and I see how the code kind of works out, but I'm not exactly sure. I think that's just lack of practice because I'm not exactly sure how I'm supposed to like do the code on my own. It's like when you first solve math problems, it kind of feels like when you see the answer key, it all makes sense, but without it, it's kind of like, oh, what? And it's kind of
Yeah,
currently in that stage.
yeah. That I think that's just like practice. Um, yeah. Uh, just to be clear, most of the class isn't like this. I'm not going to expect you to write like algorithms. Actually, these aren't really algorithms, but I'm not really expecting you to write functions. But I did say that we'll be building upon your foundations of Python and putting in practice here would be really helpful for like later in class. So it's totally fine if you don't get it right now, but and I guess it's kind of fine if you actually no, I don't know about that, but that's okay. As long as you can follow along and understand the basics of what mean squared error is, that's fine. So you're okay. Both of you guys are okay. And I guess, does anyone know what I did here for the second implementation?
I can see. I mean, like I can try. So first you import a numpy. So that means like that's for arrays, right?
Oh,
So
what's a numpy?
it's just a module that helps with arrays. So you got like, I mean, lists and arrays. List error equals numpy dot subtract label and predict. So I think that like wait, what does like dot subtract mean? Does it mean like you subtract the all of label values versus all of predict values?
Yeah.
And then I think you square all of that. That's what np dot square means. And then you return the mean of that.
Yeah.
So you just used like so what we used above, you just like you just imported numpy and just like you just like used all of their like methods instead of the for loops and everything.
Yeah. That's essentially what I did. NumPy is a really helpful package. And next week I'll be like teaching you some basics about it. But for now, we'll stick, that's just like the thing we'll be doing. I think class ends at 12, Andrew. So yeah. So that was fun. I guess we can like test to see if it works as well.
When you say import numpy as np, does that basically mean you're like giving it a variable, kind of like that?
Yeah, I'm giving it like a new name.
Oh, okay.
It's like shorter to write. Yeah.
But why do you do np dot subtract labeled pred? What does that mean?
Oh, so like np is the package. So np dot gives you a bunch of functions or new functions to use.
That's kind of confusing. I don't really get that.
Have you ever like used, are you like, do you, oh, okay. I guess do you have any experience like Java or anything like that?
I only took like 2 inspirED classes for Java, so not much.
Well, okay. So you have, so we have like, so there are packages in Python, and these packages can do some really special things. And we'll go over this next week, but oh, it's 1:37 where I live right now. So that means Andrew, class ends at 2 for you. Oh, I sent that to the wrong person. Okay. Actually, that's not EST. Okay, you know what I mean. Sorry. Okay. So we have like, okay. So I think everyone understands what mean squared error is doing, right? And so it's kind of a good, loss function to understand, especially with linear regression, since it's so easy to code theoretically, or easy to understand theoretically, since it's just minus, like taking the difference between the label and the prediction, squaring it, and then taking the average of all across all the examples. And then that's just like a number. So I guess here's the thing. If you didn't change like your weights and biases, who had the lowest loss? So for me, I had 32.0, right? So my loss was 147. Can you guys like put your losses in chat or say them out?
Wait, how do we run it?
You can run this like a solution. So just click the run cell. Then you can like do this.
Wait, how do you put in like the losses that you got? Like, does it automatically do that?
Yeah,
You
it'll
did
like
that.
it'll take if you ran W1 and B, it'll take these numbers and automatically put them in here.
Oh, I see. I got 163.35.
Okay.
Okay. Let me run this. I got 183. It's kind of a lot.
I got 160.063 or around that.
Nice.
Decimals are like really long.
I guess to
What makes the loss like less? Should I be moving my line downwards a little more? Because like I wanted to connect the first and last dots, but then I realized, oh wait, I'm leaving more than half of the dots on the other side of the line. So I guess that makes it less accurate.
to minimize this loss, you'd want to do something like this, right? So you have like if you connected like this line and this line, like you'd be like really good for the first and last ones, but that's not necessarily you wouldn't be very close to like the second, third, fourth, and fifth.
Okay, yeah, I got 162. Well, 161.6 now. So yeah.
Okay. This is pretty hard because actually, 147 for 100 samples, and you're also squaring them, is pretty good. So you're like, because you're squaring the differences, and squares can get really high. Because if you're off by 10, right, for a single number, actually it's a mean. So that's actually not very good. Actually, it's fine. By most standards, on average, we're off by like 12. At least for me, I'm off by 12 points on average. But for you guys, you're off by
I'm off by like
13.
13.
I mean, that's fine. 12, 13, that's fine. It's an error. But just for, yeah. MSE is like rarely used anywhere else, but it's like a baseline. And now we'll answer Julia's question earlier, which was, how do computers use this, right? So we have, as I explained earlier, the goal of machine learning models is to minimize loss, right? And so we just performed the iterative way of reducing loss, which is by randomly inputting different weights and biases and seeing, oh, is it lower? Is the loss lower, right? Yes, we did by eye, but a computer can use our loss function and get a numerical value saying, oh, I was lower than before. Oh, I was lower than before. It's that kind of stuff. Although, as you can all tell, it's so random, right? We're essentially guessing and checking. And so that's the kind of method that wouldn't work in the real world. So we have to try something better. In comes gradient descent. And so for the regression problems we'll be analyzing, when you graph the weight, WI, and you graph loss, you get a very interesting curve. I mean, you get a parabola essentially.
Wait, so what is weight? I still didn't understand that.
So if you, for all possible like values of W1, or like the slope, right? The slope of the line, for all values of that, like from, I don't know, like -10 to 10 maybe, and you graph that across the loss, you get a function that looks like this, where essentially there's a point where you give a certain weight and the loss is minimized, essentially. That's what's really key. It's not about the shape. Okay, I guess the shape matters, but it's not about what it looks like. But the key is that there's always a minimum loss that you can achieve. And at that value, your model is converged or it's perfect, essentially, right? Does it make sense?
So weight is the slope?
Yeah, but we're graphing like all possible values of W with the loss it gives.
Okay. All right.
And so, as we said, there's a minimum, right? And that minimum is the best value that the weight can have. Since, as always, we want to minimize loss and minimize our error. And when we find that, that means we've found the best fitted model, since it is the minimized loss. So what we could do is we could calculate the loss function for every single feature, which is kind of what we did before. We'd calculate this curve, and then we'd find the minimum in the middle, which is what we did, right? We put in random values of W, and we found like points on this graph, but we never found like the actual minimum.
Oh,
And so, as we said before, it would take a really long time since there are so many possible values for W. Right?
okay, but how come like the slope is a curve? So loss can be positive and negative?
No, loss is
I'm pretty
always
sure loss was only
okay.
is always
I mean,
positive, right?
if we
Here,
put
oh,
like 0 down here, it's always positive. Like loss is always positive, but the slope, like the slope here doesn't really compare to anything that we've done before.
okay, wait. Okay.
It's totally fine. You don't have to be worried. Like keep them coming. It's fine if we, go over.
I'm gonna just like ask my parents or search up what weight is because I still don't get the definition.
Oh, okay. I can do that. Weight is the slope of our linear regression curve. That's all it is for now.
Okay.
And when we make this graph right here, we're saying that there are multiple values for what our weights can be, but there's a certain value of a weight where the loss will be minimized, or will be the lowest possible loss. Do you understand
Okay.
like that portion?
I think so.
Okay. Okay. And so the idea here is that gradient descent is a very popular method for reducing loss. And we start by choosing a random value for W1. So this could be 0, it could be any randomly generated number. It's just a randomly generated weight. So this is like our figure here. So we just randomly choose one,
Okay.
and this is a starting point. And so we chose something slightly greater than 0. So we start here. right? And so I won't talk about like what we're actually doing here, but imagine like a ball going down a slope, right? It'll roll, it'll start really fast, right? Since you're going down the slope. And then when you're going down the slope, you'll go down to the middle, like you're in a valley. Let's say that you're in a valley. So you start really high up and the ball rolls down the hill. And at some point, you might like go in between the bottom of the valley, but over time, gravity will pull you to the lowest part of the lowest part of the valley. And that's what gradient descent is doing. We calculate the slope at that point. And that'll tell us not only the magnitude of the slope at that point, but it'll also tell us the direction towards the minimum, which is key since we need to point towards the minimum. And so there's an arrow right there describing what that gradient is. So gradient here is synonymous with the slope of the function. And so we use that gradient and step down the curve. So we have the gradient and we step down. We have the next point, and then we do like the exact same thing. We keep on doing this step thing, or this step kind of function or step method. It's a better word. You keep on stepping down the curve until you reach the middle. And that's what gradient descent is. The math, unfortunately, is really complex. But when machine learning models are calculating loss and reducing it, this is one of the best ways to do it. You step down like this loss curve until you reach a point where the loss is minimized and you get a value for W1 where the loss is minimized. Does everyone understand what we just did? As the big thing to understand is that we're stepping down this curve until we reach the minimum. It's not necessarily the math, but stepping down.
Okay.
Awesome. The next key idea, sorry, is the amount we step by, right? So this is called our learning rate. And it's called a hyperparameter, and that's something that we tune in machine learning. So hyperparameters are variables that programmers fiddle with to create good models. And so a small learning rate can take forever. Like we step really small, and it might take us like 1,000 steps to reach the bottom. But we'll reach there eventually, right? It just might take a really long time.
Well, once it reaches the bottom, doesn't the machine like stop going back up?
Yeah.
Okay.
But a really small learning rate could mean that you might be training for something that should take only a minute. You might be running your model for 10 minutes, right? Something like a 10 times longer training for models that might take days. That's like 1 day compared to 10 days. And 10 days is a lot longer than 1 day, right? So like a small learning rate would take forever, but it would reach there eventually. So the converse to that has a larger, oh, I put the wrong thing. Okay. Wrong picture. But essentially, if you have a too large step, you might go down here, and you might go across the bottom, never actually hitting the middle that you want to hit. And the perfect learning rate always exists, and you just step and you step and you step until you reach the middle efficiently. So does it make sense? Learning rate is the amount you step by.
Okay.
And so as you know, practice, I found this cool thing. It's kind of cool. I think it's cool. So there's like this, it says UCLA. UCLA is pretty cool. And so you can try this, and you can try, does this even work? Okay, set up. So we have iteration 5, then our minimum is like somewhere here, right? You can be like step. Like that. So that's kind of what grading descent looks like. But that's a good, I want you to use this website and answer these questions, these 4 questions for homework. Actually 3, because 4 is a bonus.
So it is on the same page, right? And we just finish it for homework.
Yeah, you can just write them in here.
Okay.
Double click and write them here. Oh no. Don't do that.
Okay.
Don't do that. Wait, how do I get that back? That's not good.
Wait, so you can't do like Control Z?
I messed that up. Okay, you know what?
That didn't
That's
happen to our side, did it?
No, it didn't.
Okay.
That's bad. Could someone send me the? Okay, that's fine. I'll think of it later.
I guess you could just go look at our assignments and then you'd find a copy.
Yeah, I can probably look in your assignments and get it from you guys. But yeah. Any questions on what gradient descent is? What it's supposed to be doing? Remember,
How come the step gets smaller every time
oh, okay.
on that diagram?
That's because the slope is getting smaller over time, right? So here the slope might be 1, but as you reach the bottom of a parabola, the slope gets closer and closer to 0. And so since it's going closer and closer to 0, the step over time moves like the step is smaller and smaller over time as well.
Okay.
So how can you measure these steps on the learning rate? Okay. The steps on the learning rate. Okay, so learning rate. I guess. So measuring the steps, that's kind of like that's a good question. You can't really calculate it from the learning rate since every graph is different. It's more of a thing that you, like try out. So that's what I'm expecting you to do here is like set the point, right? And then like click the next iteration, like a bunch of times until you like reach and it says like iteration 14. Hey, that's the answer to the question. Also, thank you. You now see how I make these for you. But yeah, it's 11:48. You are technically free to go if you would like. Thank you, Nathan, for that. And if you have any more questions, you can stay around. I'll be here for some time.
Bye. Thank you.
Bye, Nathan.
It says to like set a rate of learning rate of 0.03 on the slider. Like what slider?
Oh, wait. No, there's no slider.
So what do
It
we
used to
do?
be a slider, but just put 0.03 in here.
Oh wait, so we're supposed to click the link.
Yeah.
Ah,
Oh, there's no link. Okay. I'll put that in there.
oh wait, for us there is a link. I just skimmed through it and then I didn't look at the link yet. So
Oh, okay. Yeah, last night I was trying to actually let me turn off the thing.